Welcome to this Explainer by Forge College. I am absolutely pumped to have you here today. So, in our last Explainer, we laid all the groundwork for exactly why Gulfstream had to be added to the Solana network. We talked about latency, we talked about network overhead, and really just the sheer need for speed. And look, when we say speed in the context of Solana, we're definitely not talking about a brisk jog here. We're targeting up to 65,000 transactions per second, with block times hovering around 400 milliseconds. I mean, that is literally the blink of an eye. At those blistering speeds, standing around waiting to figure out where data needs to go, yeah, that's simply not an option. So today, we're taking a massive step forward. We are moving from the why to the how. We're going to roll up our sleeves and look at the actual nuts and bolts engineering schematics of how this forwarding mechanism works under the hood. Okay, let's dive into this.
Here is our quick game plan for today. First, welcome to the relay. Second, Gulfstream architecture. Third, rules of the road. Fourth, tracing a transaction. And we'll wrap it all up with key takeaways. Simple as that.
All right, jumping right into part one, welcome to the relay, or building our mental model.
Now, before we get completely lost in the code and all the different node types, we really need a solid mental model. Because let's face it, if you just try to memorize technical jargon without visualizing the actual process, it's going to feel like a giant puzzle with missing pieces. So I want you to picture a relay race. Think of the upcoming slot leaders, the validators scheduled to produce the next blocks. Think of them as the runners on a track. And the transaction you just submitted from your wallet, that's the baton. Instead of waiting until a runner arrives at some central meeting point to stop, grab the baton, and then start running, this scheduled network does something brilliant. It's layered right on top of the leader rotation, and it proactively hands the transaction progressively forward to the next scheduled runner before their segment even begins. The baton pass happens seamlessly while everyone is already at a full sprint. And this is huge because it shifts all that heavy data propagation work much earlier in time, distributing the effort across the network so no single runner ever gets weighed down.
To put that into perspective, think about the old way of doing things, waiting at a central global mempool. In that scenario, a single leader faces a massive, heavy network discovery burst right when their slot begins. Imagine, say, 10,000 impatient transactions all shouting at once in this chaotic, disorganized room demanding to be included in the next block, all while that 400 millisecond clock is aggressively ticking down. It is a massive bottleneck. The Gulfstream approach, though, radically different. Proactive pre-positioning in a local leader queue creates a highly organized relay team. The baton is placed directly into the runner's hand right as they start sprinting. No waiting around, no screaming crowd, no bottleneck. Just an orderly queue of pre-verified data, absolutely ready to be stamped into the ledger.
Moving right along to part two, Gulfstream architecture, and the core components that make it tick. Let's actually look at how this builds into the real hardware and software running the network. There are four distinct parts making up this engine. First, the client RPC endpoints. These are essentially the entry gates where your transaction is initially submitted from a decentralized app. Second, the forwarding nodes. Think of these as the middle managers. Actually, make that the highly caffeinated middle managers of the network, relentlessly sorting and passing things along just to keep the assembly line moving. Third, we have the leader scheduled data source. This is basically the master timetable, the absolute source of truth that dictates exactly who is producing blocks and when. And fourth, the per-node transaction queues. Honestly, these queues are the unsung heroes of the entire architecture. They protect the poor, overworked leaders from getting absolutely flooded right at slot time. By managing the flow of incoming data, these queues ensure the leaders don't just crash under the weight of a sudden spike, allowing them to strictly focus on what they do best, processing computations and producing blocks.
Which naturally brings up a really fascinating engineering hurdle. When you really think about it, how on earth does the forwarder know exactly where to pass the baton next, right? It's easy to say, oh, just send it to the next guy. But in a globally distributed network of thousands of nodes, achieving that kind of consensus instantly is no small feat. It's not magic, it's just a really strict set of deterministic rules. And as a quick aside, if you love mapping out complex Web3 concepts like this, you should know that the learning programs at Forge.College go incredibly deep into the architectural logic behind these exact systems. But for our immediate mystery today, let's uncover how the forwarder actually makes that critical routing call.
That takes us to part three, rules of the road, the routing decisions. Now we've got to look at the logic and control signals that govern whether your transaction stays in the relay, moves forward, or just gets dropped entirely. Whenever a node receives a transaction, it acts kind of like a ruthless bouncer at an exclusive club, strictly asking 4 questions. Number 1, freshness. Is it fresh or is the block hash too old? Number 2, target. Who's up next on the schedule? Number 3, priority. Is it actually valuable based on the fee per compute unit provided? And number 4, backpressure. Now this last one is absolutely crucial. A node literally has to ask itself, do I actually have the CPU and memory resources to handle forwarding this right now, or am I choking? If the node is overwhelmed, well, backpressure kicks in and it drops the transaction just to save itself. Each answer directly shapes the routing action. Pass all 4 checks? Come on in, move forward. If not, you're out on the curb.
Now, what's really interesting about this slide is that this lifecycle state table is essentially your ultimate diagnostic map. Developers absolutely lose their minds trying to figure out why a transaction was dropped, and the truth is, this matrix right here holds the answers. It shows us exactly where delays or failures can happen in the pipeline. Say a transaction fails at the submission state, well, you likely have a bad signature or a stale block hash right out of the gate. If it drops during staging, the forwarder's queue might have evicted it just because you didn't attach a high enough priority fee. And if it makes it all the way to the leader queue but still isn't included in a block, the leader's local inclusion policy might have dropped it because it hit its absolute compute limits. Mastering this map is exactly how you go from just randomly sending data into the void to actually engineering highly reliable Web3 applications.
Okay, part 4, tracing a transaction from start to finish. Let's make these abstract mechanics incredibly concrete by actually following a single transaction, our baton, from submission all the way to confirmation. And keep in mind, this entire sequence we're about to walk through unfolds in milliseconds. Imagine you submit a transfer transaction at slot 1. Step 1, submission and validation. The RPC checks your signature and makes sure the block hash is fresh. Let's say it passes the bouncer. Awesome. Step 2, staging. The RPC stages it in the forwarding queue. It attaches a time to live, or TTL, firmly tying its expiration to the upcoming targeted slots. It also calculates a priority score based on the fee you attached. So at this exact moment, your transaction is just sitting at the forwarder, completely packed with its metadata luggage, totally ready to travel. Then we hit step 3, the forwarding hops. Let's say validator A is scheduled to produce a block for slot 3. Right before slot 3 even begins, the forwarder proactively routes your transaction to validator A over the network. And then, step 4, leader inclusion. This is the triumphant moment. Validator A's slot officially starts, and because of that prepositioning we discussed earlier, the validator doesn't have to wait around to receive your transaction. It simply pulls it, along with massive batches of others, directly from its prepositioned local queue. It executes them all in parallel, which is what drives that incredibly high transaction per second metric we talked about, and just like that, your data becomes a permanent part of the ledger.
But we do also have to look at the alternate ending here, and I'm going to give you a little tough love. Step 5, expiry and eviction. What if validator A's block was already completely full of higher priority transactions? What if validator B couldn't fit it either? Well, eventually, that time to live expires. And when it does, the transaction is actively and aggressively evicted from all forwarder and leader queues. It's completely dropped. Now, while that sounds terrible if it happens to be your transaction, you really have to understand that this eviction is a critical feature, not a bug. This necessary cleanup is exactly what prevents unbounded memory growth. It stops stale, irrelevant data from endlessly clogging up the network pipes and ensures the entire blockchain doesn't just grind to a screeching halt.
By mapping all this out on a temporal journey, the sheer efficiency of the architecture becomes completely obvious. Slot 1 is that submission and staging phase. Notice that the forwarding hop happens pre-slot 3. That's before the leader even steps up to the plate. By the time slot 3 actually arrives, your transaction is already waiting patiently in the local queue for inclusion. And if it misses its window, the post-TTL expiry just sweeps it away. And this brilliantly illustrates how prepositioning completely smooths out the timeline, shifting all the heavy lifting away from that hypercritical, time-sensitive moment of block production.
Finally, part 5, key takeaways and our general rules of thumb. Let's summarize and really lock in your new operational reasoning skills here. If you're out there building a decentralized application or you're monitoring a validator node, these 3 principles should be your North Star. First, prepositioning is a fundamental trade-off. Yes, it absolutely saves the leader from being crushed, but it puts incredibly heavy demands on the forwarders and the network links connecting them. Second, routing isn't just random. It's tightly driven by the schedule, freshness, and those priority rules we went over. And third, memorizing those lifecycle states allows you to actually predict network behavior under high throughput and pinpoint exactly why a specific transaction failed along its journey. So the crucial point is really mastering this balance. I want to leave you with a final, somewhat provocative thought. Think about the butterfly effect in complex systems. If you are operating a node and you decide to tweak the TTL, or maybe you adjust your specific priority thresholds, how drastically do you think you'll shift the entire system's latency and reliability? Changing just one seemingly small variable in this intricate relay can cascade through the whole network, entirely altering how fast data moves and who gets included. We are going to explore exactly those profound trade-offs in our next explainer. Until then, make sure to visit forge.college to continue mastering advanced Solana concepts and dive into more world-class Web3 learning. Thanks so much for joining me on this Forge College explainer today, and keep building.